Hello guys. Today I'm going to talk a little bit about the decision tree IP that I made several months ago. Well, in my opinion, the modifications that you have to do with this IP are not that straightforward. So you will have to pay attention to a few things. So um, this is what this video is about. So let me first open the decision tree overlay that I've built so you get an idea of what has to be done. So let me open the project first. So if I go to pink decision tree, this is a GitHub repo that I've downloaded from my GitHub repo. So if you let me find that repo for you. If you're not sure, um, it's here. So this is the pink decision tree GitHub repo. So you can find it at this location. Um, so I will just go to this local repo, local copy of the repo. So I'm right now inside the pink decision tree repo. So if I go to the pink decision tree, I think not the Python, but the actual hardware project. So I go to pink Z1, um, and in the overlay folder, I have the project already built. So for you guys to rebuild the project, you just have to run the makefile there to make sure that you can build the original block design. So let me go to the decision tree, the Vivado project. I can actually use Vivado followed by the project name to open this project. So make sure that you're on 18.3 because I've just updated the flow to 18.3. So um, there are a couple things that I've already fixed. So let's first have a look at the block design there, and then we can open kind of the IP, and I will go over the flow to make it like a um, doable, like make a working IP with the pink framework. So by saying that, I actually mean this IP has an AXI interface that can be directly cooked up with the PS. So in the pink framework, you can directly call the DMA driver to, read and write from any buffers allocated on your DDR. So let's wait for the Vivado to open the project. Open block design. Um, let's have a look at the block design. So this project has already been implemented. So as I said, you have to run the makefile to make sure that you can um, build the bitstream. So if you look at this design, it's pretty simple. So you have a processing system 7 because I'm building this on Pink Z1 board. So you will have pretty much the same PS setting as shown in the base overlay or logic tools overlay. So as you see, the HP0 port is connected to the memory interface, and this the well PS is driving it. So well, it's driving the master interface of the AXI interconnect. And for the AXI interconnect, it has two interfaces. One is connected to the master. Well, if you can see this, let me zoom in. This is a memory map to stream. So, because the PS or the processor access the memory mapped address, so it has to get all the data there are memory mapped. So you have to kind of connect that data to the memory map to stream interface. And on the other hand, for your pipeline, for your IP to produce the data, it has to be converted back to the some format that PS can be uh, working on. So it's the stream to memory mapped interface, as you can see here. Well, this block is AXI memory, direct memory access. So AXI DMA basically handle, well, it's pretty, it's just like a bridge between the PS and the DDR memory. So it's connected to, well, although you can see it's connected to the PS or processing system, it's actually connected to the DDR because there are several, well, the PS block is not as that simple shown here. It has a lot of like other components in it as well. So the DMA, then, there are two kinds of ports that are connected to the actual IP. Well, the most important thing is you have access stream to, this is the output side. So the input side, you are connecting the XCDMA memory map to stream into the um, slave XC stream interface of your IP. So this DMA is actually driving data into your IP, and the results produced by your IP is consumed by the slave interface, stream to memory mapped interface of this XCDMA. So you just have to follow this kind of connection. So if you want to build your own IP, you probably want to do what you want to do is just replace this one, but follow this kind of the same connection. So this is like a very simple design, but for most cases you will have to follow this pattern. And then another interface from XCDMA is you have to kind of provide some control information to this to your IP because there are some additional control registers that you want to write into your IP. So this is driven by the S00XC. It's not XC stream, so you only see XC here. So I will see how you, internally how you handle those data uh, just in a second. So let me close this because we don't need this. Maybe, yeah, let me make a screenshot so later we can see this block diagram again. So I think this is the most important part. Okay, close this. Okay, so there's already an IP there, but what I'm going to do is I'm going to, follow the same process how I constructed this IP. Um, so you guys know what to do. So I already copied the binary tree IP here. So the binary tree 1.1, I copied from the GitHub repo to here. So if you go to the binary tree there, you see the, like a standard structure for any packaged IP. But what I'm going to do is I'm going to just borrow those source code, but I'm going to create a new repo. So let me see if I have it somewhere. No. So I'm gonna make a new dir a directory, like a C. Let's call it binary tree project maybe. Okay. What I want to do is I want to open a Vivado here, and I'm trying to create an IP there. Um, so remember that we are inside the binary tree project folder. Okay, so let me create a new project. Next, project name. Let's just call it project one, because once the IP is packaged, I don't need to keep this project. So I'm gonna just use this. You need to choose RTL project, add files, because well, we don't have the source code. We haven't write anything, or we haven't written anything, but I just borrow the source code from the binary tree. So I add those three thing into the project. I also want to copy sources into project. So if I make changes, I don't want to screw up with my old original code. Um, so I click next. Constraint, there's no actual constraint. And for parts and boards, I guess we don't have anything special here. So just make sure you have all of those supported. Yeah, it's okay that it shows like some warning that no constraint files will be added. That's fine. We know that. Um, okay, let's see where the okay it's adding the source code. So an interesting thing is when you add the source code, the structure will be processed automatically. So, well, actually, I have three pieces of code. The top level called binary tree.v, and in lower levels, you have first stage.v and middle stage.v, as you can see. So let's see what is going on inside this. So, well, the binary tree on top is taking some parameters and as well as some input and output pings, right? So this is a very standard Verilog code. So I'm not sure if I can zoom in. I cannot. Yeah, so this is pretty standard because for different levels, so my default configuration, the binary tree only has three levels. And you have certain number of bits per field or per index. So let me show you what I mean by that. So go to decision tree. So if you look at this tree, there are three levels in this example as well, right? And then there are several fields like weather or condition. Condition is another field. Day is the third field, age is the fourth field. So there are multiple fields. So you need several bits to represent the field, to kind of encode the fields, right? So you have four fields, then you need 2 bits. If you have 8 fields, then you need at least 3 bits, right? So that's the meaning of number of bits per field index. Well, per field index. Yeah, because you have the field index like 0, 1, 2, 3. So for 4 fields, you have them indexed as 0, 1, 2, 3. So you need 2 bits. And then like the parameter number of fields is like um, 2 raised to the power of number of bits per field. So if you have 3 bits for each field, then you have like 2 to the power of 3, which is number of 8 fields, right, for the decision tree. And then number of bits per field is 8. So you can have like 2 to the power of 8 different values in each field. So that's quite a lot because you're also representing the value in each field by a binary digit. So um, if you have 16 different values in one field, then you need at least 4 bits to represent those, 0, 0, 0 all the way to 1, 1, 1, 1. So that's what this parameter is about. So total number of bits is number of fields times number of bits per field. So it's basically indicating how long your packet is, right? So, well, if you can imagine that your data is coming, um, you know, with multiple fields and you have multiple bits per field. So your, the total length of the input is indicated by this equation. So you have total number of bits as the input packet length. Number of stages, like I think this is the same as number of tree levels, or maybe or plus a one or minus one. But this is a you know has is directly related to the number of tree levels. Then you have a lot of inputs. I don't want to introduce this too much, but basically what it does is um, when you're given a packet, right? It kind of parse the first field, and then based on the first field, you construct whether it's going to the left branch or the right branch of the tree. So you're kind of constructing the address based on the input, right? So if we can see the tree, so if the first field you have matched with Sunny, then you probably go 0 to the left branch, or you go 1, you output a 1 for the right branch. So as you go along this tree, you will have construct an address of, for example, the first leaf node, you will have 0, 0, 0 if mark the left branch as 0, right? Similar for the rightmost leaf node, you have 111 as the address indicating is the last leaf node. That's what this tree is doing. So address O, is the final output when you are kind of searching the tree, right? So there are a lot of good things to have a look in this one. So basically, it's kind of a little bit complex because everything is parameterized. So you have to make sure that at each stage you have the correct number of inputs and correct number of outputs. So there are some numbers of some parameters that you have to figure out during this coding design. So this is the top level binary tree, and why do I have two lower level codes? One is first stage and the other is middle stage. First stage is a little bit different because you get the input from the input header, like the first field, but you don't have any well you don't have any other input address coming to you. So maybe I can introduce the middle stage a little bit better. So if you like the middle stage, like the second or the third level of the tree, so it's not only it's not only taking the input from the packet header, like from a specific field of of the value, but you also have to combine it with the previous address. So, for example, if the previous stage produces a 0, you have to combine it with your the result of current level. So this branch is 0, 0, right? Um, and if you are here, then you're kind of combining the first level result and the second level result into 1, 0, right? This is a 1, this is 0. So in the all the middle stages, you will have to kind of pipeline the input, kind of combining with this the current output, and then you know um, pipe it through to the next stage. But for the first stage is very different. You can see it doesn't require any input from previous levels because it's the root level. So you only have to parse, kind of match the current level. So, So that's the difference. So it took me like 2 or 3 days to develop this piece of code. But for more complex problem, you may have to do spend more time here. Or if you have already some IP verified, then that's easier for you. But I think what's more challenging is you have to kind of have your own test bench to simulate it before you can put it onto the Python framework, right? So you need to make sure the hardware actually works before you can build the bitstream because it saves you time. So I have to write my own test bench and run simulation. But for some reason, I cannot find the simulation test bench in my code. So let's assume that this one is already working. So you have to kind of make sure that you test the other corner cases because um, there are another challenge here. You need to make sure that with um, certain control registers set, you will have to load the original data for the decision tree. So if you check this, um, if you check this one, it's not only the pipelining of this input and output that takes me time, but it also takes you some, some effort to make sure that at some point you are able to load the data into the tree. So suppose you have, three levels, then probably you have a three-stage pipeline here. So three-stage pipeline, you will have to make sure that with a certain load level, like load signal, that you can load all the data into this decision tree. So basically, the first RAM has, can produce two outputs, 0 or 1. But at the second level of the tree, it can produce its four possible outcomes, right? 0, 0, 0, 0, 1, 1, 0, and a 1, 1. And the third level is well, it can produce eight different outputs. So, um, so on and so forth. So you have to make sure that each stage you have enough memory to store the next stage pointer or next stage result. So yeah, so you will have to kind of make sure that you are also able to load the data into this one as well. So that has already been taken care of in my original Verilog code. So let's close this. Um, what I'm going to do is I'm going to create and package new IP once I have all the RTL working. So, well, before that, let's have final look at this code. So you have, when you design your IP, you have to keep in mind that what control registers that you want to have. So, for example, when I design this input and output pins, I'm already making assumption somewhere in my paper that the data is something that I want to put into AXI stream because it's something sent by the PS, right, through the AXI DMA, and the output address O is like um, the output like the index of the leaf node that you located through the tree. So you have this number. Well, this is the has to be mapped to the axis stream for the output of the binary tree, and data is should be mapped to the input of the binary tree. And all the other inputs, I think they are just some control registers that you have to figure out during, some preparation stage, right? And when you there are some signal like load. If you put load too high, then the tree is reading the data into every node. But when the load is 0, you start to match the input against the tree. And then some valid in and loss in um, signals that are important to the XC stream. So basically, you are passing valid signal along with the data. So you are making sure that when you produce the data, you can check the valid in or the valid signal to make sure that you are read the data is actually a good data. So if valid is low, then the data is garbage. You can discard it. You can discard it. Um, so that's something interesting there. So let me go to the next step, create and package new IP. So I'm going to create a new AXI-4 peripheral. Make sure that you have this selection because you are doing some AXI stream AXI IP. So the name I can just call it. Well, let's make a difference than my decision tree. I'm just going to call it my IP. I'll just choose this regional thing. Um, Click next. So at this stage, you will be able to select the number of interfaces. So by default, it has at least one slave interface, which is AXI light interface. So AXI is not AXI stream. So perhaps this is good for the control registers. I will have, well, I will choose that, but I will also need to add two more interfaces. One should be axis, well, the other two interfaces have to be axis stream. So make sure the 32-bit slave, so you can actually see that on the left side. You have that. And then I need to add another, which is also axis stream. This has to be master. So you end up with something like this. So you have axis light interface for control registers and axis stream for both inputs and outputs. So let's continue. You will need to choose edit IP and finish. Vivado will open another project for you to edit your IP, so you can keep the original project untouched. So as you can see, it's opening a different project. There are many things tricky there. We will have to carefully go through this. So by default, some additional interfaces or some additional RTL code has been added to you. Sorry, added to your IP. So if you have a look at this, you have S00XC, which is for your XC Lite, and two XC stream interfaces. So if you look at this S00XC, which is for your XC Lite interface, you will see a lot of interesting code, and you can, it actually has some comments like ask you to add some user parameters or user ports, right? Uh, I think what you need to pay attention to is that those slave registers that you can check can be actually modified or added into your design. So in this default example, it only has four slave registers, but I don't remember how many I'm using, but you can add more, um, and you can, let me see, you can actually add the ports. So when you write the XC light registers, it actually um, gets fed into the fed into your RTL code, the original IP. So let me try to find the original code. This is the well, this is the original code or the code I modified for the XC interface, right? XC Lite interface. So I think I've added some parameters there, as you can see. Some input and output. The program field is let me remember. I think it's um, well, I don't remember what this is about, but um, it's something that the RTL code will take, I think. So I'm actually using 16 registers, slave registers, if you remember that in the original code there are only four. Well, by the default code, uh, the default code only has four. So if you have to make modifications there, um, I think there's a place. So most of the code can be just simply change this code. Initially only has four, slave register 0 to slave register 3, but it's very easy to be able to extend this code to 16 registers. So let's see. So the user logic is here. That's something I've added, and it's very important. So basically, you need to make sure that you're using those slave registers, right? So for example, I'm loading the address in address I, which is like always zero or always one. Load is a signal which enables your IP to load the data to the decision tree nodes, right? And reset is like resetting everything to zero, and it's taking those we are taking those signals from the slave register, the first three bits, right? And then some other signals I'm taking because sometimes it's very long um, data width, so you have to take multiple registers. Like in this case, I'm taking four registers, it's like 128 bits, right? 'Cause each register is 32 bits, you have four, then this one is taking 128 bits, and the next one is also taking 128 bits from another four slave registers, right? By this way, I'm using up to slave register 12, but I'm not using all of the 16 slave registers, which is okay. Just make sure that you have assigned enough bits to, something you want to output. So I think finally, you see, this is like an intermediate signal, but I'm just taking the correct number of bits from this intermediate signal. So that's the slave register. Have a look at this one. It's very easy. So I think this add user logic here is the most important thing that you have to make sure. So let's go to the slave. So a slave of axis stream. So axis stream slave is is corresponding to the input of your decision tree IP, right? Because something else is driving it, so it's the slave interface. If you look at the original code, um, there are a lot of FIFO and stuff there. I'm not using this piece of code. I'm rewriting it to my own favor. This is it's same for the master of the access stream. So I will just ignore those two, default code generated by Vivado. Let me open what I have done. So if you check this code, I only put four signal for the AXI stream interface, like the T data, T valid, T ready, and T last, which indicates the whether it's the last data of your uh, data burst, right? The same is for the AXI output. So basically, this is well, this is I think this is a asynchronous IO, asynchronous FIFO. So you have the read pointer and the write pointer. Basically, if you um, remember, the asynchronous FIFO, you have two clocks, one on the reader side and one on the writer side. So writer side is the input. So whenever you receive a data, you put it into a FIFO, and then you increase the write pointer by one, right? And for the output side, you have a reader pointer. Whenever you consume or you take one data from the FIFO, you increase the read pointer by one. So, there's also some logic to determine whether the FIFO is empty or is full. But you have to make sure that since it is asynchronous FIFO, you have to do double sampling um, on the read or write pointer, I think. So those are implementing this. So have a look at this. It's a very interesting piece of code. You can borrow this, and I think it won't change for a lot of your IPs. So if you design your own IP, you can just simply take this, right? All you need to make sure is that you have the correct parameters somewhere in your code. So the parameters determine, sometimes it determines the data width. So that's something you have to make sure. But other piece of codes are very straightforward for this. Um, so for the master, it's the same, basically replicated. Um, and it's not very long, and it's not the same as the one generated by Vivado, but it will simply work, right? So I don't want to go through this. This is also another way to do this, but I don't like this style, so I wrote my own piece of code for slave or master access stream interfaces. So after you debug this, you just have to I think you can just go here, package my IP, or if you accidentally close that, I think you can just double click the IP dash X act. So you can just double click the component.xml, open this. So you have some parameters to figure out here and there. Um, and then compatibility, you need to add more. Basically, for our pink IP, we usually add the zinc and zinc ultra scale family, but the easiest way to make sure that it works for every device is to add all the families there. So you can add family explicitly and click all of them, right? And you can also choose the lifecycle. Here, I want to skip this and want to make sure that you have some customized parameters. Sometimes those parameters are not that important, so you can just hide those parameters. And for some parameters that you want users to configure when they instantiate your IP, you can expose this, and when you edit parameter, it allows you to choose like how you want user to select the value. Like, do you want to have a list of values or range of integers or pairs of strings or something. Description, format, editable dependency. You can have a look at that. It's not that hard. Ports and interfaces. So since your IP, um, if you remember when we packaged this IP, we already selected those interfaces. So you don't have to do a lot of things for ports and interfaces unless unless you have not selected the XC to package the IP as an XC4 IP. So in that case, you will need to kind of select multiple lines. You will see basically multiple lines there. Not in this case, but you will see in other IPs that you have multiple lines and you want to group some of the lines into a specific type of interface. That's something you need to consider. But for our case, we don't have to change that. Address and memory, just use default. We don't have to do anything. And you can have a final look preview of your IP. So as you can see, there are multiple parameters that can be configured because we didn't do much thing here. All right, we didn't do many things here. So you can try to expose certain parameters there. after you, after you satisfy this review and package IP, you can just put it into a zip file, right? So I won't do this. I'm gonna just exit, don't save. Just save. I want to close both of the projects, right? So this is the IP flow. Then after your IP is ready, you can just open your Vivado project as I showed you at the first place, right? So it's the pink decision tree overlay. So if I go to pink decision tree, sorry, not derivative overlay. Oops. Well, yeah, I just almost forgot. Have this. So basically, you connect your IP to your block design. Then you have everything ready for your hardware. Then for your software, you have to do a few things. You have to make sure that when you are preparing the data, you need to make sure that you write data into certain places that your IP is going to fetch. For example, um, the slave registers, right? So when you are preparing your tree, you need to make sure that you are loading the data into slave registers so that your tree is going to configure itself to some state. Then next you can push data into a DMA buffer. So the DM buffer is going to push data to the AXI stream interface. So your pipeline is going to process the data and return it back to the PS. So if I look at this, the final thing that I want to show you is the source code of the decision tree. So I actually have software version and hardware version. I'm just going to show the hardware version. I'm going to increase this. So that some input parameters that you have to um, take, and then I think, let me see, I think a register is the place. Yeah, so this is making sure. So if you look at this, so have some internal functions to you know um, get node bits, get field bits. So to process the data and make sure that I can set it to the tree. So there are something interesting there. Because the way I'm writing the slave register is your binary tree will have an base address which corresponds to the MMIO, which is mapped by the MMIO class. And when you're doing this overlay, the pink is able to figure out the base address of your IP. So if you have a IP block tree control, then in your overlay you will have self.tree control, and then you can just write into the base address, just provide an offset with the values to it. So you will be able to configure the the slave registers, right? So if you do write 0 uh, 123, then you are able to write 123 into the slave register 0. But if you write 4, if you put this as 0x4, then this and another value like 2, 100, then you are able to write 100 into slave register 1, right? Because it's byte addressable. So 0x4 corresponds to the second slave register, which is slave register 1, right? So 0x, so on and so forth. 0x4 corresponds to third slave register, and then every slave register is going to be the next 0x4. So in that way, you can configure the slave register. And well, you see a lot of code there, but it's not that hard. You are just going to make sure that you are writing some data into it. So that's the kind of tricky thing. So I'm going to make another video later about how to do a very easy example in step decision tree, because I think decision tree is still a little bit hard for starters to get a sense. So perhaps I'll get another video. So please be patient and hope you enjoy this video. If you have any questions, feel free to ask me or leave any comment. Thank you and have a good weekend. Bye.